Hey, what's up, guys? Okay, so previous video that I showed the Turan theorem. So Turan's theorem says that if G has KR plus 1 free, so basically no complete graph with R plus 1 vertices, then the number of edges that at most 1 minus 1 divided by R plus small 1 and choose 2. Or basically it's the following. Again, previously that we used mathematical induction to prove, and now we are going to use another method, basically very shortly, called the probabilistic method. Okay, so this probabilistic method proof is the probability proof of Turan theorem. Okay, so this type of proof is a very powerful tool in the combinatorics and also number theory. Okay, so the idea is the following. Say G is a vertex and edge. And consider the probability, right? So we should consider sigma, which is a random ordering of the vertices. So basically, this is just the following map, right? So this is 1, 2, up to n. So this sigma is a random ordering. Random ordering of vertices. Okay, and we consider X as a set. So basically, in order to prove this, we need to create some clique. So the idea is that the V belongs to V, where V is earliest. So V is connected to all earlier vertices. Okay, probably this sentence is hard to understand. But basically it's the following, right? So let's say you have V1, V2, V3, this is your order, V4. And then you can maybe V1 connected it, and V2, and V3, maybe you have V6, something like this. Okay, so V1 is chosen, right? And then V2 connected to all its vertices. So V2 is chosen, V3 connected to all its vertices. No, right? Because V3 connected to V1, but V3 don't connect to V2. So V3 is not, and V4 is not, right? Because V4 does not connect to V3. Okay, so the situation is that if you collect a set of X, it contains, let's say, Vi plus 1, Vi plus 2, they become like this. So we need to connect it to all the early vertices, right? So it's become this, right? So all the X, all the vertices in X will connect it to all these early vertices. Okay, so this gives you following. Basically, X is a clique. Okay, so we can ask what is the expectation value of X, right? So expectation of X basically is the size of X. Okay, so basically it's you consider all the V belongs to the vertices, the probability of V belongs to X. Okay, now this side, since X is, this graph is KR plus 1 free, right? So the size of the clique must be less equal to R. And the probability V belongs to V basically is the following. Basically, it's your V, right? Need to connect it to its all early vertices. So basically, this means that all the early vertices must be V's neighbor, right? So, so basically it says following. Basically, it says that all the early vertices, or the earlier vertices, must be V's neighbor, right? But this is the same as uh all the vertices which is not V's neighbor. V should be the first one. Okay, so V should be the first one among all all vertex which is not V's neighbor. Okay, so basically, for example, you have 1, 2, 3, 4, 5. This is V. And then these 4 points, these 4 vertices should not be for V because V do not connect it to these 4, right? So V should be the first one among all vertices, which is not V's neighbor. So the number of vertices, which is not V's neighbor, is what? Is n, right? Total vertices minus degree V minus 1, right? Because minus V itself. Okay, so the probability V belongs to V is 1 over n minus degree V, right? Because V should be the earliest one, right? So the R is greater or equal to summation V belongs to V, 1 divided by n minus degree V. Okay, and notice that this function is convex in terms of degree V. Okay, so this means that if you have a convex function, basically it says that if your summation of xi from 1 to n, you can replace by its greater or equal to its average, right? So average will be just n of f of summation xi from 1 to n divided by n. Okay, so this will greater or equal to n minus summation of the average, right? So it's v belongs to v where degree v divided by n. So it's n minus divided by n minus the sum over degree v. So this is the 2 times the edges. So this is the handshaking lemma. So 2m divided by n. So we have this. So we have r greater or equal to n divided by n minus 2n divided by n. So r greater or equal to n divided by n minus 2n divided by n. So we can solve the n, right? So basically you do this, then you immediately show the following. So you have this. Immediately prove the following. Okay. So this is the second proof of this Turan theorem. See you guys next videos.